Welcome to Temperature Relations. This chapter is going to look at organisms maintaining body temperatures, responding to heat or cold in the environment. And we're going to start with an extreme creature here called a wood frog. Wood frog. This critter is found in Canada, the northern U.S., and all the way up into Alaska. When you think of frogs, you don't think of cold or winter, right? Our frogs here go to the bottom of ponds and lakes, bury themselves. Toads will bury themselves under leaf litter or in burrows. But when you go up further north, it gets so cold for such a long period of time that the vast majority of amphibians, like our frog here, they just can't tolerate those winters. And yet, these guys are able to tolerate winters all the way up into Alaska. And so how do they do it? Well, they literally freeze. 70% of the frog's body is frozen. The water inside its tissues becomes ice. But what they do in their cells is they secrete a glucose antifreeze, which, due to osmotic pressures and other stuff that you don't have to worry about knowing, it prevents the actual cells from freezing and losing their functionality. And so once it warms up, the frog thaws and comes to life in the span of, I want to say, minutes to an hour. It doesn't take long. But they can freeze during the winter, which is a pretty cool adaptation that most amphibians do not have, at least not to the degree that these guys do. So they're able to deal with that winter temperature. What is temperature? Technical definition of temperature: a measure of the average kinetic energy of the molecules in a massive substance. The faster the molecules are moving, the greater the heat within the object. That's the general idea. And so if you warm something up, you're actually speeding up the movement of the molecules and warming it up. Why is temperature important? It's important because many chemical reactions move at different speeds depending on the temperature, and many of these reactions require certain temperatures to occur at a speed necessary for life. For instance, photosynthesis is the process where plants make food using sunlight. This tree is a bristlecone pine, and that specimen might be, I don't want to give an exact number because I'm not sure, but it's not that tall. And it's 4,000 to 6,000 years old. It grows in the high mountains of the Sierra Nevadas in California, and it grows at a very, very slow rate. I'm going to look up the rate and add it into this video so that we can have the exact rate. But it grows at a very, very slow rate, and this is because it lives high in the mountains where the growing season is very short. Cold throughout much of the year for the plant to experience growth, and so it grows in very, very small increments during that growing season. And so these trees, they do not get particularly large, and they grow very slowly, and so a 4,000-year-old specimen looks like this. On the other hand, there are trees in Missouri called cottonwoods that in the span of 200 years will dwarf that 4,000-year-old tree. So it's all about what are the not only temperature, there's also the soil has an impact as well, but temperature is the biggest one. So why is temperature important? It impacts the rate of chemical reactions. We're going to distinguish macroclimate from microclimate. So when you hear the weather report, you're hearing about macroclimate. Whenever people talk about climate change, they're talking about macroclimate. Macro means large. So macroclimate is large-scale patterns. So, for instance, Missouri's part of a couple of different climatic zones, and so the temperature, the overall precipitation, all of that on a large scale throughout the state would be macroclimate. Basically it's weather averages on a global scale. Whenever you think about climate in general, this is what you're thinking about, right? Important thing to note with climate, it's weather averages, and so there will be extreme weather events, and those in and of themselves do not dictate the climate. It's the overall trend that occurs. Microclimate happens within the larger macroclimate. This is climatic variation, so variations in temperature, water availability, all that stuff that's impacted by climate. Climatic variation on a small scale. So what are we talking about? Well, here's some examples. Caves. A microclimate with very little sun exposure leads to consistent temperatures throughout much of the year. In the middle of summer, you go into a cave to cool down. In winter, you could go into a cave and you would warm up. That is a microclimate, right? Whatever the weather forecast is, it's not going to impact what's going on in the cave. Other microclimates are formed by topographic features like rocks, mountains, hills, things like that, which create a lot of microclimates. One example of microclimate can be seen with north versus south facing slopes. So let's draw a hypothetical Earth here. Here we go. And this is nowhere near to scale, it's just for illustrative purposes. We're in the northern hemisphere, all right? We're above the hypothetical Tropic of Cancer here. And so here's a hill. A hill in the northern hemisphere. Sunlight is going to more directly hit the southern aspect or southern facing slope than it will the northern facing slope. And so south facing slopes, they dry out more quickly, there's less saturation with water, they bloom, things that bloom in the spring bloom earlier in the year on south facing slopes because they're getting more direct sunlight. It's quite a difference, north and south aspect. One way you might be familiar with this is with moss. People say moss grows on the north side of trees because the south side of trees is getting more direct sunlight. The north side of trees is getting less direct sunlight, and so moss, which needs water to reproduce, can more successfully grow on the north side of trees because the moisture is retained due to less direct sunlight. So even trees offer a microclimate for moss depending on which side of the tree we're talking about. So not only with differences in north and south, but even the canopy of trees creates microclimates, right? So in the forest, it's cooler. Anybody who's ever gone hiking on a hot sunny day can tell you when you get in the shade, it feels a lot different. And so those are microclimates in the understory caused by tree canopies, rock piles, just anything that's a physical feature that's going to influence how much sunlight reaches somewhere and thus how much water is retained. All those are microclimates. Another microclimate you might observe is elevation. Here, or I should say, elevation creates microclimates. That's the right way to phrase it. Elevation creates different microclimates. Not so much in a place like Missouri. Here, we just don't have any mountains that are high enough to cause, at least to the layperson, easily observable differences. However, if you go out to Arizona, all right, I have family out in Tucson, this is what it looks like in the lowlands. As you work your way up the mountain, you go through a couple of different levels. So you have the desert on the ground, or I should say, it's all ground. You have the desert in the lowland areas. Right? So here's our little saguaro cactus right there. As you work your way up the mountain, you get oak woodlands. And then as you move your way higher, you get conifers, pines, mostly pine down there. And so it's different microclimates depending on your elevation, which ultimately has to do with temperature, right? Among other things. The temperature is the prime driver. So elevation creates microclimates. Lower temperatures, the higher you move up. There's actually skiing on some of the mountaintops down in Arizona, and you can see here, out here is the lowland desert, and then this was taken in the mountains. Aquatic environments experience less temperature fluctuation than land-based or terrestrial ones. It's because water, and we talked about this before, so I'm not going to illustrate it again, but if you want to look back at a previous lecture on aquatic environments, we talk about this. Water's heat capacity is high, which means a lot of the heat coming onto a body of water is used to break apart the hydrogen bonds in water, and so it takes a lot more heat to warm up water than it would in an equivalent volume of something else, like land, for instance. Water also serves as a heat sink, and so coastal areas tend to be more moderate in air temperature because water absorbs a lot of the heat. That picture is from Monterey, California, and if you were to go to Monterey, California any time of year, it's going to be between 45 degrees and 70 degrees for the most part. Very moderate temperatures. And that is due primarily to what's called the ocean effect, water serving as a heat sink to absorb that excess heat. All right, moving on to the principle of allocation. We've talked about this before, really like to hammer it home. All organisms are adapted to a limited range of environmental conditions. Here is the key thing with the principle of allocation. Please remember that energy is limited. It's like having a budget. You can devote money to one area, but if you do, that's less money you have available to devote to another area. Energy is limited, and all organisms, I should say different organisms differ. Different organisms differ. Wow. Organisms differ in where they allocate that energy. Here's a human example. You can be a top-notch power lifter, or you can be a top-notch marathon runner, but you cannot be both at the same time. If you're a power lifter, you're devoting a lot of energy into building pure strength. If you're a marathon runner, having that much bulk is going to be taxing on your body and on your joints, and so you don't want to have energy devoted to muscles for strength. You want to have it devoted to cardio fitness and muscle devoted to, for instance, your legs for the distance, but you don't want to be carrying a lot of excess bulk if you're going to be doing that. So you can only be truly built for one of those two. So according to the principle of allocation, as the population adapts to a particular set of environmental conditions, its fitness in other areas is reduced. Here's an example, we'll get to this part shortly. Here's an example with eyesight as our sense that we're going to look at. Top picture is a cave fish, the bottom picture is a bald eagle. Eyes take a lot of energy to maintain, so if you're in an environment without light, it's a complete waste of limited energy to spend it on eyesight. However, our bald eagle has eyesight 10 times more acute than you do, and it feeds in principle by observing organisms. It can see a rabbit. It is thought it can see a rabbit up to 2 miles away. Its vision is that acute. And so there's a lot of energy that goes into maintaining that level of eyesight. No point in wasting the energy if you're in a dark environment. And so energy gets allocated to other things like sense of touch and sense of smell in our cave fish. So how does this relate to temperature? Some organisms are more adaptable with temperature. Others have a much more narrow range. But every organism does have a limit of where physiologically it is capable of functioning. And so let's apply this principle of allocation to temperature. If you devote energy to being ideally suited for a certain temperature, perhaps through the amount, if you're an animal, the amount of hair you have, the amount of blubber that you might carry for insulation. If you adapt for a particular set of conditions, that means you will be less fit in conditions other than that. It doesn't mean you can't survive in conditions other than the optimal. It just means whatever the optimal temperature is or temperature range, that's what you are physically built for. And so the principle of allocation applied to temperature says that organisms perform best within a particular range. The reason for this is that enzymes are proteins that catalyze and allow most chemical reactions to happen. They work best at certain temperatures. Here's some examples. Sleeping. You can sleep in a wide variety of temperatures, but they found that optimal sleeping temperature for most people, and it varies from person to person, no doubt, but for most people it's 68 degrees Fahrenheit. What does that mean? Well, your body does a whole number of restorative things, your brain especially, when you're sleeping. And if you want to maximize your body's ability to perform those restorative functions during sleep, this is the temperature that you'd want to sleep at. If you sleep at 80 degrees, you'll still sleep, but it might be restless, you might wake up more, your body might not be able to get into REM sleep as much, or its rapid eye movement sleep, as it would in 68 degrees. And so ideally, this is what our bodies are suited for, at least with clothes on. 68 would be kind of cold otherwise, but that is what we are suited for. Another example is photosynthesis rates. If you've ever had a garden, you know that external temperature, as well as rainfall, impacts how large your plants grow and how big the fruit yield is. So if it's a hot, dry year, you might still get a decent number of crops, but you won't get nearly as much if it were a little bit cooler and had a little bit more rainfall. And so plants, we're ignoring the rainfall part for now because this is about temperature. Plants are going to photosynthesize optimally at a certain temperature and/or temperature range. If it's too hot or too cold, they can still do it, but not nearly as efficiently, and you'll get you'll get fewer crops if it's not optimized in terms of temperature. So everything, thanks to the fact that energy is limited, there is no organism that can survive optimally at every temperature. Everything has an ideal temperature, at least ideal range of temperatures, and usually organisms can deviate from that, but they're best suited for that particular narrow temperature or temperature range. Having said that, organisms can, like we said, adapt. You can sleep in 80 degrees, even if it's not ideal. Over time, no doubt you would get accustomed to it if you did it quite a bit. You'd never reach the same optimal benefits of this, per se, but your body would acclimate over time to where you'd be able to get more uninterrupted sleep, greater amount of the all-important deep sleep or REM sleep. And so short-term physiological adjustments are called acclimation. The key here is that acclimation does not involve the genes. It does not involve you getting a new gene for something. It just means that the genes you have allow for some flexibility. Right? So acclimation is not evolution. Evolution occurs over time. As gene frequencies change, acclimation is a single organism being able to adapt to a variety of conditions. We're going to get to the word poikilotherm here shortly. It just means something, an organism that matches whatever the environment is around it in terms of temperature. So most creatures that do that have an ideal temperature where they maximize their body's efficiency in terms of metabolic processes and stuff. But they can function even if it's cold or hot compared to that ideal. For instance, toads mate in the spring when it can get down to 40 or 50 degrees. Usually they won't actually be mating if it's too cold, but they can survive 40, 50 degree temperatures. They also can survive when it's 80 or 90 outside. Optimal temperature is going to be somewhere in between there, but they can survive a range of temperatures nonetheless, so they would be able to become acclimated to different temperatures. Is that a word? Acclimated? I think it is. It just sounds weird. Regulating temperature. All right. So if organisms are ideally suited for a narrow temperature range, any of us who live in Missouri can tell you that temperatures vary a lot, even from one day to another. So how do creatures survive in these flexible temperature areas? Most of them regulate. And here is our equation for temperature regulation. So what do all of these things mean? Let's go through it. The H sub S is the total heat stored in the organism's body. That equals the sum of all this stuff. Let's start with H with the subscript M. Heat generated by metabolism. Let's say you're going to eat a pizza. In that pizza, there is a lot of energy stored in the form of glucose, lactose, among other things. Your body has to break down glucose and the other sugars, and in the process of doing that, it's going to release some heat. So, you eat food, there's energy in the food, but your body can't actually use the food directly. It has to convert it into usable energy, which we'll talk about later. But in the process of breaking down the food, there's a lot of heat that gets released as a byproduct. So, you and other mammals generate a lot of heat through the breakdown of your food. Conduction and convection, the next two, have to do with heat transfer. Convection, let's start with conduction. Conduction is heat transfer from solid to solid. One thing my cat used to like to do was sit on top of the dryer when it was running because the heat would warm her body. That's an example of an organism warming up through conduction. If you'll notice, conduction has a plus and a minus sign because you can gain or lose heat through this. My cat gained heat. If I were to go and jump up and hug an iceberg, I would lose heat. So both of those would be examples of conduction. Solid to solid heat transfer. Convection is heat transfer through the movement of a moving fluid, and often when we think of this, we're thinking of movement of the wind. So on a hot day, a cool breeze, right? Feels good. You would be losing heat, cooling down via convection. This next one is heat gained or lost by electromagnetic radiation. So the sun provides electromagnetic radiation in the form of visible light, UV radiation, infrared radiation. All of those can ultimately provide heat. The most common of those for heat is infrared radiation, but anybody who's had a pet reptile knows that you have to put a heat lamp, and that is providing heat through radiation. And last but not least, evaporation. Heat can be lost through the evaporation of water droplets, which take heat with them as they evaporate. This is why you sweat. Right? It's a way to lose heat and cool you down after physical exercise. And so all of these, the sum of all of these, is the internal heat of an organism. So let's talk about endotherms then. That's what you are. An endotherm means inside temperature. These are critters that rely on metabolism for regulating body heat. Right? So these guys, body heat increases their body temperature to whatever it needs to remain at. Mammals are in this group, like you. So are birds. Birds and mammals both generate heat through their metabolism. It's also no coincidence then that birds and mammals are the two groups that are still active during the winter time, because even though it's cold, many species of bird and mammal are able to maintain their body heat despite frigid outdoor temperatures. And different species have different methods of dealing with that, which we'll look at some of those shortly. But birds and mammals are endotherms. They regulate their heat through their metabolism. This also means they have to eat a lot more than other animal species, because you need a lot of food to get that heat burning, right? The more food that you eat, ultimately the more heat you're going to produce. So if anybody has a dog or a cat, you feed it 2 or 3 times a day, right? You eat 3 times a day, most of you would. Ectotherms, on the other hand, eat a lot less. In fact, large snakes can eat once every 6 months because they do not use their metabolism as a source of heat primarily. Ectotherms means outside temperature, and these are organisms that use external sources of energy to regulate their body temperature. The example that we're familiar with is reptiles. So, just like you, reptiles function optimally at a certain temperature, and it's often warmer than the ambient temperature around them, and so they have to use techniques to warm themselves up. What they do is they do primarily heat transfer by conduction, and so reptiles will sit out on a hot rock and absorb the heat from the rock. Infrared radiation, electromagnetic radiation, though, is their prime heat source. They will sit and the sun will warm their body temperature, and they will sit for a while until they have a warm enough body temperature to be active, and then they'll be active during the day, retreat into a burrow or something like that at night, and the next morning do it all over again. And so you often see reptiles out sitting in the sun, absorbing that electromagnetic radiation as a source of heat. Some organisms don't regulate their body temperature at all. They don't have to go out and find a source of heat to warm them up. They match what's around them. Many fish species, like this crappie here, fall into that category, as do certain frog species, like this green frog. It's called a green frog, even though this one happens to be brown. And so these guys are adapted to a wide range of temperatures because you have to be if you're not trying to actively regulate that temperature. So poikilotherms do not regulate their body temperature. This is all great for animals, but what about plants? So plants don't move, but that doesn't mean that natural selection hasn't shaped them in a way that fits the environment they live in. We're going to look at two extremes. We're going to look at desert plants and tundra plants. Let's start with desert ones. So this is a hot, dry environment. If you're a plant, what can you do to maximize? Well, number one is have your leaves pretty high above the ground. What's the purpose in that? The higher up, the greater the amount of wind, convection cools the plant. And so having your leaves well above the ground maximizes heat loss through convection. The leaves are small, right? Less surface area, and they're reflective. They tend to be lighter in color so that they don't absorb as much electromagnetic radiation, minimizing the amount of absorbed heat. Plants will also orient their leaves to maximize wind exposure and increase heat loss by convection through wind. They'll orient their leaves so that sunlight is not directly hitting them, so they get less of that heat through electromagnetic radiation. On the other hand, plants in the tundra face the opposite challenge. It's cold, and there's not, at least for a good chunk of the year, there's not as, let me backtrack on all that. During a certain part of the year, there's abundant sunshine, even 24 hours worth of sunshine in certain areas, but it's cold. It's cold. So what do? You grow low to the ground. Right? Minimize heat loss by convection, opposite of the desert. Cluster your leaves together to minimize surface area exposure and thus minimize wind exposure in that way too. Put your leaves facing directly into the sun and have darker colored leaves to greater absorb electromagnetic radiation. So with plants, it's primarily either maximizing or minimizing electromagnetic radiation as a source of heat and convection as a source of heat. So let's look at endotherms a little bit more. These are creatures like you that use your metabolism to regulate your body temperature. All right. There is a certain sweet spot when it comes to maintaining your body temperature where you don't have to do anything to try and cool yourself or warm yourself up. It's called the thermal neutral zone. It's a sweet spot of temperature where your body doesn't have to do anything to try and maintain that temperature, other than the normal metabolic heat production. What I mean is, you don't have to shiver, your hair doesn't have to stand up, you don't have to sweat. If you get too hot, your body will sweat. If you get too cold, your body will shiver, among other things. But there's that little sweet spot in there where you don't have to do any of those. That's the thermal neutral zone. With humans, it's a bit strange because we wear clothing which throws it off. The thermal neutral zone for us is much warmer than what we're comfortable with normally, because when we wear clothes, we're insulating and we can tolerate much cooler temperatures than we would if we were not wearing clothes. Our natural thermal neutral zone is actually small, very small, and quite warm. It's about 10 degrees or so, around 20 and 30 degrees Celsius in that general vicinity. What about other creatures though? How do they compare? So here's a human, there's Morgan Freeman, and here's an Arctic fox. Its thermal neutral zone is going to go up to around 35-ish degrees Celsius, but it's going to go as low as negative 40 degrees Celsius. And so when it's negative 30 degrees up in Canada, that Arctic fox is going to experience that temperature the same way you would experience room temperature. it's just not even going to register as being cold. It does not have that sensation in that environment. Arctic creatures have a much wider thermal neutral zone than you do. They have adaptations in fur, in the amount of blubber or fat insulation that they have. You and I are still a tropical species because that is the origin of humans. So our thermal neutral zone is similar to other tropical creatures. Species that live in the Arctic, though, they have a massive thermal neutral zone, right? Way bigger than ours. And so they don't have to worry about getting cold in the same way that you and I do, unless it's below 40 degrees, negative 40 degrees Celsius. You don't see endotherms in water very much because water is a giant heat sink and temperatures are usually pretty stable comparatively. And so most things that live in water are what's called poikilotherms, which match their temperature, right? Most fish are this. Many other aquatic invertebrates would also fall into this category, jellyfish, things like that. However, dolphins, whales, seals, sea lions, etc., they're mammals, and so they are still endothermic, right? They have ways of dealing with cold, so many of these species will live in cold water environments. It's layers of fat or layers of thick fur, but it's usually layers of fat that called blubber that help these guys tolerate cold temperatures. Another method of dealing with cold is called countercurrent heat exchange. So this is a way of keeping, of preventing heat loss if you have an extremity that's sticking out in the cold, right? So sometimes if you're cold, you might huddle yourself like this. You might put your hands under your legs to minimize exposure of the cold to your hands. I find when I go biking in the morning, my hands are the one thing that seems to get really cold on the handlebars. And so it's that extremity exposed to the elements that seems to be most susceptible to this cold environment. And so many species use countercurrent heat exchange to minimize heat loss and to save energy. So how it works is warm blood going out in the artery, it's released, the oxygen within is released through capillaries to the tissues of the foot region. It's cooling down because this is exposed to the cold. Blood comes back in the vein, and the warm blood in the artery, since it's right next to the vein, it's going to ultimately release heat through conduction and convection into our vein, which is coming back. So by the time our vein returns to the main bulk of the organism's body, it has warmed up to the same temperature that it was going out. The temperature itself in the foot is going to be a little cooler than if we did it a different way. But this is energy efficient, and it ensures that by the time blood returns to the body, it is once again at that optimal temperature. This is without the countercurrent heat exchange. It stays warmer by the time it gets to the foot. It's a little warmer than it would be down here because there's no heat leaving the warm blood in the artery. But when it comes back, it just keeps getting cooler and cooler, and it's going to be half the temperature, 16 degrees. This is Celsius when it returns to the body. So countercurrent heat exchange is energy efficiency, and it helps to ensure that returning blood is the appropriate temperature. It's used in appendages, birds' feet, flippers of creatures like dolphins and porpoises, and in the foot of something like an Arctic fox, which is, I think, what this is supposed to be showing. All right. So a lot of organisms will also deal with temperature extremes by entering resting stages. Sometimes this is just a single day thing. This is a hummingbird. Hummingbirds active little guys. They can beat their wings or flap their wings 50 times in a minute. And because of how active they are, they have incredible energy needs. We're supposed to consume around 2,000 to 3,000 calories a day. If our energy needs were the same as a hummingbird, we would have to consume 155,000 calories in a day. So that's a lot of energy usage. They are moving constantly seeking out flowers or hummingbird feeders to get sugar and get energy. Torpor is when they lower their metabolism at night to the point where they're barely using any energy. It's an energy-saving mechanism. And so it's a lifesaver for these organisms whose daytime activities require incredible amounts of energy. It's not just hummingbirds. They're the most stark example, and that's why I like to use them. But other organisms do this too. Sometimes you gotta go dormant for a long period of time. Hibernation is when you do that during the cold winter months, like this Arctic ground squirrel. Now, when we think of hibernating, I'm sure your first thought is a bear. Technically, bears don't hibernate in the strictest sense of the word, because they will actually become active when it warms up, even if it's in the middle of the winter, and then they'll go back to resting again. So in the technical usage of the word, usually it's only small creatures like our ground squirrel that do it, but we often apply hibernation to anything that goes dormant during cold winter months. Some species that don't hibernate are able to beat the cold by having thick insulating layers of blubber, like our walrus there. And other species have layers of thick fur as well, like musk oxen. And some species huddle together. So during Antarctic winters, penguins, it's king or emperor penguins, I believe it's emperor penguins, huddle together, which reduces surface area exposure and warms up the penguins that are involved. And so that's one way to help minimize to help minimize heat loss, that's right, to help minimize heat loss. Sometimes you want to lose heat because it's just too hot out. And so if you cannot tolerate dry, hot conditions for most of the time, you can do what's called estivating. Estivation is the summertime equivalent of hibernation. This is prolonged dormancy during hot and dry periods. This is a spadefoot toad. This thing lives in the desert, but it's only active whenever there's a rain or monsoon. And so for months on end, even years sometimes, they just sit dormant underground doing nothing, barely having any metabolic activity. So for some of these desert amphibians, it can last for years. And it's not determined so much by temperature with them, it's rains. They need water, not only to live, but to reproduce. Other ways to survive heat is to have lighter coloration. If you've ever gone out on a hot day with a black shirt versus a white shirt, you know that the black shirt absorbs all of the colors of the visible light spectrum, and so it's a lot hotter for you to wear that. So if you got lighter coloration, you can survive better in dry and hot environments, right? Such as our little canyon tree frog here. Another simple way to do it is find a shaded microclimate like these kangaroos. Right? Simple, but effective. During the hot Australian summer days, they will not be out in the sun. You'll find them resting in the shade. Another method that we use is evaporative cooling. We sweat, and water, as it evaporates, takes heat with it and removes it from our bodies. And so not many species, to my knowledge, are capable of sweating in the way that we are, but you can also douse yourself in water and get a similar effect, right? So if you can't sweat, that's another potential way to utilize the benefits of evaporative cooling.